Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. If you check out the solar panels on your neighbor's roof or the solar farm out in the blinding Arizona desert, you'll find most solar panels are made of silicon. But silicon as a material has its drawbacks. It's expensive to manufacture into solar panels. It makes the panels really bulky, and its efficiency for converting sunlight into energy has plateaued around 26% for the last decade. Yen-Hung Lin, a device physicist at Hong Kong University of Science and Technology, is researching an alternative material to silicon for solar panels known as metal halide perovskites, or perovskites for short.
It can absorb light quite efficiently.
Perovskites are a crystal, meaning they're made of repeating units. They offer a potential advantage over silicon because they could be cheaper to produce and offer higher efficiency. They can also be made into a thin, flexible material, which makes them less bulky and easier to transport and install. People have also begun creating what's known as tandem solar cells, where they combine perovskites with silicon. The silicon is best at absorbing the near-infrared wavelengths of sunlight, whereas engineers can tune the perovskites to optimally absorb sunlight in the visible spectrum. The combination allows a solar panel to convert more sunlight into electricity, and experts have recently reported efficiencies of over 34%. But perovskites have flaws too, and Lin's research team is working to make them even better.
The problem is when we manufacture any kind of material at such a low cost and low small budget, we can't get rid of defects.
One common type of defect in perovskites are vacancies, where certain subunits of the perovskite crystal are missing. The defects make the perovskite less efficient and less stable. To understand why, let's break down what happens when sunlight hits the perovskite. The photons from the sunlight excite electrons in the perovskite from the valence band into the conduction band. This basically separates charges in the material into negative electrons and positive holes. To get the solar panel to produce an electric current, you have to separate the electrons from the holes.
If we don't take electron and holes out of the material, naturally they will recombine.
To make electricity flow through the material, you want to prevent the negative electrons from recombining with the positive holes. But these defects encourage this undesired recombination.
They are actually acting like a hole, basically to suck this charge carrier in.
Lin's group found a new way to reduce defects in the perovskite. They treated the perovskites with a category of molecules known as amino-silanes. These molecules bind to those vacancies, preventing recombination. To assess how these molecules improve the perovskite as a solar cell material, the researchers also measured specific electrical properties of the perovskite. When a photon hits the material, it separates the negative electron from a positive hole. And this separation creates an internal force that pushes the charges apart, generating electricity. Stronger internal forces mean the solar panel can produce more power. Lin's team discovered that the force driving these charges was about 90% of the maximum level predicted by thermodynamics. In addition, the amino-silane treatment made the entire device more robust to the environment.
They basically form a very strong layer protecting perovskite underneath.
They also tested the amino-silane treated solar cells' performance over time. They found that the devices could maintain 95% conversion efficiency in open circuit conditions for more than 1,500 hours under full spectrum simulated sunlight. The devices were also kept at 85 degrees Celsius in relative humidity of 50 to 60% in ambient air.
This is the very important assessment for photovoltaic cells stability.
This work was published in a recent issue of Science. My name is Sophia Chen from the Materials Research Society. For more news, log onto the MRS Bulletin website at mrsbulletin.org and follow us on X at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.